Another problem up here. E is the solid unit sphere. A solid sphere is sometimes referred to as a ball, so I could also say this is the unit ball. S is its boundary, oriented out. My vector field is 3x, 4y, 5z, and I want to calculate this, which would be the flux of F across S. Now, I could certainly do that as a double integral, but we've seen that parametrizing the sphere, we usually would work with spherical coordinates as our parameters, the two that aren't constant on the sphere, so theta and phi. And it's not super hard, but it's time consuming and kind of tedious. So sometimes when you're working with a surface like the sphere that has a kind of long, complicated parametrization, the divergence theorem can be kind of nice. According to the divergence theorem, this is the triple integral over E of the divergence of F dV. So let's calculate the divergence of F. The divergence of F is del dotted with F. So that's going to be the partial with respect to x of 3x, plus the partial with respect to y of 4y, plus the partial with respect to z of 5z. Oh, this is nice. That's going to be 3 plus 4 plus 5. That's 12. So I'm doing the triple integral over E of 12 dV. If I'm integrating a constant, I'm just going to get 12 times the volume of E, because if I factored out the 12, I'm left just integrating 1, which would give me the volume. Now, if you happen to remember the formula for the volume of a sphere, you can use that, because here it's showing up as part of a larger problem. So I can say this is 12 times 4/3 pi times my radius, which happens to be 1, cubed. I'm just going to write that so we don't forget that's an important part of the formula. Awesome, that's just going to be 16 pi. So what would have been a very long problem to do by the definition of flux and by working with the surface integral is actually very, very fast using the divergence theorem. Now, that happened to be particularly nice because my divergence was a constant. That won't always be the case, but it can sometimes be a big time saver.